Good evening, ma'am.
Okay, so let's start our today's session. We'll be discussing some previous assignment problems. Question number 1. Denote Rn square to be a collection of all n cross n matrix. Which of the following functions defined on Rn square is differentiable? Then functions defined on Rn square is differential. First one is the determinant matrix, determinant function. So we define f from Rn square to R. F of A is just the determinant of the matrix A. Or then we have the transpose map. That is our function f. So transpose of a matrix is again a matrix. That means we are mapping a matrix to another matrix. Our function is from Rn square to Rn square. F of A is just A transpose. Then the third one is for a fixed matrix B, or a fixed n cross n invertible n cross n matrix B, we define a function which is depending somehow on B, again from Rn square to Rn square. Every matrix A is mapped to B inverse. Then the fourth one, the trace of the matrix. Now, since trace is a real number, trace map. That means f is from Rn square to R. F of A is trace of A. So any guesses which of the following functions should be trivially differentiable?
Determinant here. It is a polynomial.
Since it will be eventually polynomial of these n square variables.
Yes.
And rest of the three options, they basically come under same criteria, and using that condition you can see that it will be differentiable. All you need to notice is that the rest of the three options are all linear transformations.
Yes.
And we know that every linear transformation is differentiable. And what is its derivative? Derivative of a linear transformation, linear map, is always the map itself. So at any point, the derivative, we know that dfx, dfa, this should be a linear map. And when our function f is linear, in that case, dfa is always the same linear map, if you remember.
Yes, ma'am.
So we'll see how we get that. I'll do one example for that. Rest options will be exactly the same one. So I hope this is clear that both the second, third, and fourth option all are linear transformations.
Yes, ma'am.
Because transpose, and this is just the third part. These are called the equivalent matrices. No?
Yes.
So
Trace is
eventually,
also.
trace is also linear. So everything is just linear. So okay, so firstly, we know that if we define the function f
And ma'am,
from
how we see this determinant as a polynomial?
that's a tricky task. But eventually, we know how to find determinant. The determinant is eventually depending on the variables, the points in the matrix. So suppose if f of a, we are defining this as f of some matrix a11, a12. Here, all ai's are variables. Hence, we have n square variables. So yeah, its general form is quite difficult to express, but eventually everything will be a polynomial, polynomial with the variables, all these a1, 1 to a n n. So eventually up to a n n. So this will be a polynomial with n square variables, or a polynomial of degree. Degree will also be n square. So eventually, since we know that every polynomial is differentiable, in fact, it is infinite times differentiable. So the function is differentiable. Yes, differentiable. Next, let's look for the transpose map. If we define f from Rn square to Rn square, f of A is A transpose. Now we know that f is differentiable at A if and only if there exists a linear map dfa from Rn square to Rn square such that f of a plus h, this is equal to f of a plus dfa at h plus eh, where e is such that upon norm h, this goes to 0 as h goes to 0, and this happens if and only if limit h tending to 0 f of a plus h minus f of a minus dfa h upon norm h, this is equal to 0. Yeah, for some linear map dfa, all we need to find is such all we need to find is a linear map DFA which satisfies this condition. Now this linearity of the function f will come into the picture. See here, fa plus h minus fa is nothing but a plus h transpose minus a transpose, which is eventually h transpose. So if I define dfa from Rn square to Rn square such that dfa maps any h to its transpose, which is basically the same function. This dfa is the same transpose map. Then limit h tending to 0, fa plus h minus fa minus dfa at h upon norm h. This is equal to, so the numerator is 0, so eventually everything is 0. Now since this is a linear map, therefore f is differentiable at a belonging to Rn square, and this is happening for every a in Rn square with the derivative dfa is the transpose map which is equal to f. So I can write it as equal to f, and this is happening for every a in Rn square. So this is a good result to remember, that every linear map is differentiable and its derivative at each point is the map itself. So similarly, you can see the third and fourth part as well, because eventually we'll get something like this, and using this we can define df at a. So is it clear? If you have
Yes,
any
ma'am.
doubt.
Yes, ma'am, it is clear.
Okay, okay.
Second.
Let's move to next question. In this problem, we identify the set of complex numbers with R2 in the obvious way. That means if we have a complex number z which is equal to a plus iota b, so we'll write it to be equal to a comma b. This is an element in C and this is an element in R2. Okay.
Mm.
Let f from C to C be differentiable. Then the derivative map, they are saying that we have a derivative map at 0, df0 from R2 to R2, and then it can be viewed as a map T from C to C under our identification of C with R2. So what we have, we already know that df0 from R2 to R2 is a derivative map. That means this is a linear transformation. Then we are saying that we define T as our identification. That means for any complex number z in C, t at z, this is equal to t at some a plus iota b, and this a plus iota b will be what we say, identified as a comma b, and then we'll apply the map df0 at a comma b. So this is what they mean by t is taken from C to C under our identification. So t at z, this is equal to df0 at a comma b, and
Okay.
our range map. Sorry, we can see that the codomain of t is C. So this, instead I should write it as, so this will eventually be a complex number. So this is df0ab. Now this df0ab is an element in R2, so it has two components. So we take it as the first component plus iota times df0ab at the second component of df0. So this is how we define T. We are defining T using the map df0. df0 is a linear map from R2 to R2. So for any point Z in C, obviously Z will be of the form A plus iota B. Then we want to use the map df0 to define T. Now T has the codomain of T is C, the set of complex numbers. So we define it in this way. Because uh, the first component denotes the real part, and the second component denotes the imaginary part. So is it clear how this T is defined?
So df0 is a map from R2 to R2.
Yes,
So
df0
here
at
we
point
see this.
AB. This will have two components
Oh, yes.
because it is from R2 to R2. So this first component denotes the real part, and the second component denotes the imaginary part. So that's how this 1 and 2 denotes the first component and second component.
Okay. Okay. So df0ab1 is
The first part
it
component.
belongs to R, not in R square, I think, na?
Yeah, both these terms. I think there is some lag. Yeah, both these terms are real numbers, but our tz should be a complex number. Na? Using this,
Mm.
suppose we have a x comma y. This is x comma y, so I'm writing it x plus iota y.
Yes, yes, okay.
Something of this form.
Okay.
Okay, then the options are something related to this map T.
Mm.
Then now df0, we know that this is a derivative map, so it will always be linear. We need to see when is this map T linear. Then firstly, they are saying that T is automatically complex linear. By complex linear, we mean that our field is to be is taken to be the set of complex numbers. T is never complex linear unless T is the zero map. T is complex linear if determinant T is positive. Let the matrix of df0 be A, B, C, D, then T is complex linear. If and if A is equal to D and B is equal to minus C. So by complex linear, we mean that T alpha C plus T alpha Z1 plus Z2, this should also be equal to alpha T Z1 plus T Z2 for every alpha in C, because we are talking about complex linearity, and Z1, Z2 in C as well. So for this, the idea that comes into mind firstly, because already we know that df0 is linear. So in case of real numbers, everything might seem very easy, and you might think that the map T will eventually be linear. But the problem will occur when we multiply the uh, complex number z by some iota, by iota. So let's see what happens in that case. So let z equals to a plus iota b be some complex number. Okay, let's start with pointwise. We'll see the additivity firstly. Z1, Z2, then we have dz1 plus z2. This is t a1 plus a2 plus iota times b1 plus b2. And by the definition of t, this is equal to df0 at a1 plus a2 comma b1 plus b2 का first component plus iota times df0 a1 plus a2 b1 plus b2 का second component. Now since df0 is a linear map, since df0 is a linear map, we have df0 at a1 plus a2 comma b1 plus b2. This is equal to df0. This can be
A1
written
B.
a1 comma b1 plus a2 comma b2, and this will be df0 a1 comma b1 due to linearity as df0 at a2 comma b2. So now these are two vectors.
X1 Y1 X2 Y2.
Yeah, I can write it as df0 a1 b1 for first component plus
Mm-hmm.
bf0 a2 b2 for first component comma
Mm.
0 a1 b1 for second component plus
Plus
bf0 a2 b2 for second component. So that means df0 a1 plus a2 comma b1 plus b2, its first component is equal to df0 a1 b1 plus its first component plus df0 a2 b2 its first component, and df0 a1 plus a2 b1 plus b2 second component. This is equal to df0 a1 b1 second component plus df0 a2 b2 second component. So using this, we get dz1 plus z2. This will be, so I'll just club the iota part. So this, the real part will be df0 a1 b1 first component plus iota times df0 a1 b1 second component plus df0 a2 b2 second component plus iota times df0 a2. So first component a2 b2 second component, which is nothing but dz1 plus dz2. So from this we can see that it is closed under addition. Therefore, we don't have any issue when it comes to addition. That means there might be some issue for the case of scalar multiplication. Now, you can check it yourself. For alpha belonging to R, T alpha Z will be equal to alpha times TZ. Similarly, as we have done the addition part, you can
Mhm.
see it yourself.
Yes, this alpha will go everywhere alpha.
Yeah, again you will be using the linearity of the map df0.
Yes.
Then the problem will happen when we take this alpha to be equal to iota. And let alpha is equal to iota. Then t iota z, this is equal to t iota a plus iota b, and this will be t minus b plus iota a. So this will be df0 at minus b comma a first component plus iota times df0 minus b comma a second component. And iota times dz, this is equal to iota dA plus iota b, which is equal to iota df0 at a comma b plus iota first component df0 at a comma b second component. So this will be minus df0 a b at second component plus iota times df0 a comma b first component. Now if the map T is linear, then in fact you can see that for any other complex scalar, if this condition is satisfied, then eventually it will hold for every complex number. From here we can say that
Is equal to C.
T is linear if this df0 minus ba first component
Is
is
equal
equal
to
to minus df0 ab second component
mm,
df0 times this is minus ba second component. This should be equal to df0 ab first component. These two conditions should be satisfied in order to make the map T complex linear.
mm.
Now suppose our df0. Now df0 is a linear map from R2 to R2. So we can denote it with a matrix of order 2 cross 2.
Yes.
Now, if this df0, suppose this is equal to x1, x2, x3, x4, all xi's are real numbers. In that case, what will be df0 at minus b comma a?
Minus bx1 plus bx, so ax2,
Minus bx1 plus ax2
bx3 plus ax4.
minus bx3, no?
Yes, b
Minus
man.
x3 plus
Yeah.
ax4. This should be equal to minus df0 ab. Okay, what will be df0 at ab?
ax1 plus bx2, ax3 plus bx4,
Ax1 plus bx2, then ax3 plus bx4. This implies our map T will be linear
if
if the first component of this is equal to negative of second component of this. That means minus bx3 plus ax2. This is equal to minus ax3 plus bx4. And similarly, minus bx3 plus ax4 is equal to its first component ax1 plus bx2. So eventually, you can simplify this. From here, you'll get that a times x2 plus x3. This is equal to b times x1 minus x4. A times x4 minus x1. This is equal to b times x2 plus x3. So this should happen for every a, b, and r because, yeah, z equals to a plus iota b was an arbitrary complex number. These x1, x2, x3, x4 depends on the derivative of the map f at 0. So eventually, if f is such that the derivative, these xi satisfies this system star, in that case the map will be linear. But the first option is saying that T will automatically be complex linear. So can we find some example where this is not becoming linear?
mm,
Just some example, take some fixed values of x1, x2, x3, x4 such that both the equations does not hold simultaneously or any one of them is not holding.
and minus bx3 plus ax2 equal to minus of that, how
Sorry, this is
bx3 bx1 plus ax2, I think.
the second equation, this one.
First,
The first one is df0 minus the first component of this one minus
अच्छा
b.
वो first and second component.
Uh-huh.
So in value of x naught to
So can you find some x1, x2? If we take f such that df0, this is some matrix, then star does not hold and eventually the map T is not linear.
So we need to take a matrix which is invertible, I think.
No, invertibility is not necessary. df0 is just a linear map. All we know is
Okay.
that the function is differentiable at that. It need not be invertible.
Oh, okay, so three items equal.
Your voice is not clear. Can you please explain?
No, no. Oh, sorry, ma'am.
Okay, it's
Doing
okay.
rough work. Ma'am, if we take any matrix
Your
and
voice
then solve
it's
these two
not clear.
equations, then
Sorry. Can you please repeat?
now if we take any matrix here,
Hmm.
and then we solve these two equations above,
Hmm.
then we will find a relation between A and B. So
Yeah, but
that
this should
relation that
happen for
for
every
all,
AB.
yes,
And we
and
want to show that this is not happening for some
mm,
example.
so if we take another A plus iota B, then that is not hold in that case.
Mm-hmm. So
So
give me
that will be contradict.
some example of fixed x1, x2, x3, x4. What x1, x2, x3, x4 I should take so that this won't happen. Any
So if we take
example?
1, 2, 1, 2, 3, 4, if we take
Okay, if you take 1, 2, 3, 4, then what is happening? A times x2 plus x3, 2 plus 3. This should be, suppose this is equal to b times x1 minus x4, 1 minus 4. A
mm,
times 5, this is equal to minus 3b. Yeah, this might not happen all the time, but yeah, but this might happen for some also. So it's better to go safer side. Yeah, this is also fine because in order to get it linearity, this should happen for every AB. So what I took was 1, 0, 1, 1. In this case, if we look at the first equation, A times x2 plus x3 is 1 plus b times x1 x minus x4 is 0. So that means A is equal to 0. Eventually, yeah, that is also showing that for we cannot prove it for every AP. Yeah, any such example would work. All we need to show is that T need not be complex linear.
mm, wow.
Okay, so it is fine that this is not complex and linear. In fact, we'll see that when it can be linear.
Okay.
Second part says that it is never complex linear unless T is a zero map. So can you find some matrix DF0 such that this will hold and the map is not a zero map? That means you need to find a
Mm,
matrix DF0 such that this star holds, this system star holds, but this is not equal to the zero matrix.
okay. So we solve this two equation, I think. Then I can find.
Just try to look for some trivial examples
Okay.
that might work.
If it is identity matrix,
Okay.
mm, A is equal to no, shit. Mm, okay, so this plus this and this minus this. This will be equal in it. Mhm.
So a hint would be fourth option.
Mhm. And B equals. Okay. So this identity, I think it also
It will
satisfies
satisfy.
the fourth option.
Yeah, yeah. Because everything will eventually be zero in this case, no?
Hmm.
Identity is a non-zero map that is satisfying the conditions. Therefore, the second option is also incorrect.
Yes.
And by whatever we did above calculation, it is clear that fourth option is correct. From here, we can directly say that this fourth option is correct. Because if we take x1, instead of x1, x2, x3, x4, they have taken a, b, c, d. So if we take x1, x2, x3, x4 such that x1 is equal to x4 and x2 is equal to minus x3, in that case, all the terms will be eventually zero. So for every a, b, this system star will hold. So from here, this is correct. Next, we are left with the option third. Option third says that T is complex linear if determinant T is strictly positive. But from
This
first
from
page
there.
also, you can see that this example, in fact, this in this case, this is four. This is negative. But yeah, in this case, the determinant is
Oh, negative.
of. Okay,
Yes,
so we
positive.
are talking about determinant of T, not that of F, DF. That is also a difference. T is a map from C to C. What do we mean by determinant of T?
The second option, ma'am, it says that
Second option.
T is never complex linear unless T is zero. Second
Yeah,
option.
T is zero. So they are saying that if T is zero, then it is complex linear. Otherwise, it cannot be complex linear. But we have shown an example where T is non-zero. Using this df0, you can find T. Eventually, this T will be non-zero, but still, the map T is complex linear.
Oh, here
So
df0 is non-zero, so T is also non-zero.
yeah, yeah. Using this df0, you can find.
Oh, because these two are
This is just
identified.
identity map, na? So eventually this will make tz equals to z.
Oh,
This
oh
is
yes.
identity map. So using this df0, you can find t. This t is a non-zero map, but still it is linear. They said that it can be linear
Yes.
only if it is zero map. So therefore, the second option is incorrect.
Yes, okay.
Okay, next we are saying that t is complex linear if determinant of t is positive. So what I could understand from here is that suppose T is a map from C to C, and if it is a linear map, we can denote it with a matrix. So when we have a vector space C, and we are talking about complex linearity, so I hope this is C over C. In that case, the basis for the space of complex
One in iota.
so complex over complex. That's the
Uh,
difference.
uh,
In that
uh,
case, the basis will be just one. And
one.
B, this matrix will be just a one cross one matrix. So determinant would be
Hmm.
this component itself. And this will be T of one, this term.
Hmm.
We have, so by definition, we have T from C to C and T at any point A plus iota B. This is equal to df 0 AP first component plus iota df 0 AB second component. This implies T of 1. T of 1 will be df 0 at 1 comma 0 first component plus iota df 0 1 comma 0 second component. So the determinant they are talking about is the simple determinant T is the determinant of the matrix T1. Now that they're saying that T is complex linear, although this seems a bit tricky because if the map is linear, then only we can talk about its matrix representation. T is complex linear if determinant T is strictly positive. Now, if I define, I'm saying that this is not true. That means there exists some T such that the determinant will be strictly less than equal to 0, but still it will be complex linear. So if we take if suppose df0 was the zero matrix, in that case, our T from C to C is it will eventually be the
Zero.
zero
Zero
map.
map.
But we know that zero map is also linear, na?
Oh, yes.
T of 0, this is 0. So the matrix corresponding to this linear map T will be 0 matrix and its determinant will be 0, which is obviously less than equal to 0. Therefore, we get a contradiction. Hence, this is not.
So
Yes.
image of one is the determinant of each matrix here, no?
So eventually, that is what coming because we our vector spaces are just one dimensional. So from one
Yeah.
dimensional vector space to one dimensional, so eventually the matrix would be one cross one matrix. And we know how we define this matrix. This is just column wise image of the basis elements. And when we are taking a vector space of complex numbers over the field of complex numbers, in that case our basis has just one element, 1. When we are talking about C over R, in that case this is a two-dimensional vector space
into
with basis elements 1 and iota. Whereas in case of CC, this is a vector space with one-dimensional vector space with basis element just 1.
okay. So, so value of determinant, ma'am, is it real or also depends on the field
Value of determinant depends on
or
field.
field? Okay.
Yeah, obviously it will depend on the field. Because if suppose we had some
Determinant of 1 plus
imaginary
iota
elements,
will be what? Is it 1 plus iota
it will
itself?
be 1 plus iota.
Oh, okay, okay.
So I think this is what I got, because but this still seems a bit tricky, because there one side they are saying that it is, we can find its determinant, and then they are asking about linearity, because when T is a linear map, it is sure that it is corresponding to some matrix. Maybe there might be some printing mistake that this determinant T was actually determinant of TF0, but if
Hmm.
it's determinant of T, then it should be like this.
Yes, no.
Okay, therefore the fourth option is correct. Okay, next we have some application of inverse function theorem.
Hmm.
Which of the following statements are true? First one, any C1 smooth function f from Rn to Rn whose derivative is invertible everywhere is an injective map. Injective means one to one. Then we have any C1 smooth function f from Rn to Rn whose derivative map is invertible everywhere is a surjective map that leads on to. Then we have if f from Rn to Rn is a C1 smooth map whose derivative map is invertible, invertible everywhere, Then this is from nRn to Rm. Then n is equal to n. And the last one, any C1 smooth map f from Rn to Rn, whose derivative map is invertible everywhere, is a local diffeomorphism. To solve this problem, we should be well aware about the inverse function theorem and the definition of diffeomorphism. So let's recall the inverse function theorem. It says that suppose f is a function from U, which is a subset of Rn, to Rm, be a C1 mapping, and DFA, the C1 means it's differentiable everywhere and the derivative is continuous as well. So that means DFA is well defined. And moreover, if this DFA is invertible, then we have the following. So the conditions that are required for the function f should be a C1 map, and at point A, this DFA should be invertible. Then we have firstly this Rn is equal to Rm, or we can say that n is equal to m. So this directly gives us this third option.
Option
From
is
here,
correct.
third option is correct. This is just an application of inverse function theorem because our function is C1 smooth and its derivative is invertible at all the points. Okay. Then our second point says that there exist open sets V subset of U, W subset of R, M, such that this
N
A
is
belongs
in
to V, f of V, this is equal to W. That means the function f restricted to V is a map from V to W, and this is a bijection.
in yes.
1, 1, and 1. Okay, then our third point says that if we denote, now since this f restricted to V is a bijective map, that means it is invertible, denoting its inverse to be G equals to f restricted to V inverse. Then this G is also C1. G is also a C1 map with the derivative of G at any point y. This is equal to
Inverse of
dfgy. Now this dfgy is a linear map. We take its inverse. And this is happening for every y in. Y will belong to
RM.
W
RM.
or
So
W
W is
because G is inverse of f restricted to V.
derivative of inverse is inverse of derivative.
Then we have the definition of diffeomorphism.
Hmm.
diffeomorphism and local diffeomorphism. It says that if f is a function from U, which is a subset of Rn, to V, which is again a subset of Rn, be a map, we say that f is the K diffeomorphism if, firstly, f is Ck on U. That means it is k times differentiable and its kth derivative is continuous as well. Then f,
Derivative is continuous or partial derivative is continuous?
all the partial derivatives. So yeah, when we are talking about just r, in that case we say the derivatives.
Derivatives.
F is bijective. Then f inverse is also ck. Now since f is bijective, so f inverse is well defined, and this inverse should also be ck on b. Then we say that f is local ck diffeomorphism if for every x in U we can find a ball such that f restricted to that ball satisfies the above conditions. We say f is local ck diffeomorphism.
It becomes local property. Okay.
Hmm. It depends on the point. For any point, we can find some locality around it. Diffeomorphism.
Mm.
If for any x in U, we can find ball be ball around x bxr contained in U such that f restricted to bxr. Now this is a map from bxr to suppose some subset of b. This is a ck diffeomorphism.
Mm.
So now, if we combine these two, we can see that if f is a smooth C1 smooth map, suppose f is C1 and its derivative is invertible and dfa is invertible, then by second point of the inverse function theorem, we can find a ball.
It's local discrimination.
Eventually, we'll get the local diffeomorphism. Because by second of the inverse function theorem, there exists an open set V subset of such that F restricted to V
Is
is,
bijective and
yeah, this will be eventually C1 diffeomorphism, no?
Mhm.
C1 diffeomorphism. And in fact, since V is open, we can find a ball as well. Because, yeah, if we
Mm.
want to go by exact definition, and since V is open, this implies there exists a ball. B,
B
suppose we are taking
A
at x, B, x, R. So yeah, we can take it at A also. Yeah, B, A, R contained in V such that F restricted to this ball is C1 diffeomorphism. And since this is happening for every A, because according to point fourth, we know that our function is differentiable at every point. The derivative is invertible. Therefore, since A belonging to Rn is arbitrary, we can say that F is a local C1 diffeomorphism. F is local C1 diffeomorphism. So from here, our fourth option is correct. So therefore, till now we know that the third point and fourth point are correct. First and second are saying that this will be everywhere injective or everywhere surjective. So locally we know using the inverse function theorem and the definition of diffeomorphism, eventually we know that locally it will be injective as well as surjective. Eventually that means in fact bijective. But we cannot say anything about the whole domain. So can you look for some example? Try to find example in. So let's start with a real valued function. Uh,
Ma'am, there how restriction of F on ball is also C1.
restriction of ball. Sorry. From here.
Restriction of F.
Yeah,
Mm,
because restriction of F over V was diffeomorphism, na? So V is an open set. We can find a ball inside V, and
mm,
since everything is happening in V, so it will be happening inside the subset also, na? The 3 points that we need, it should be CK. It will be CK on a subset also. It should be bijective.
oh,
Bijective, obviously, from BAR to its image, whatever the image is, it will be eventually bijective.
oh yes.
And inverse will also in the similar way. Since it is happening on a bigger set, I took this just for the sake of definition because in the definition it was said that at every point we should be able to find a ball.
Okay, ma'am.
Otherwise, because from inverse function theorem, we are already getting an open set, which is I would say a better condition.
Mm,
So now we'll try to find some counter example for point first and second. Firstly, I would like you to find a function f from R to R such that its derivative is non-zero for every x in R, but f is, or we can say, and f is not surjective. Because when we
it
are
to
from
be
R to R, the derivative being invertible means that the function, that means the at every point the derivative is non-zero.
non-zero.
So
So if we e to the power x,
yeah, exactly. So if we take fx to be e to the power x, we know that this is not surjective because this will never take the negative values. F
also
is
it is never zero.
surjective, yeah, never zero. Is not surjective, but f dash x, this is e to the power x, this will be never zero for every x in R. Therefore, our second point is incorrect.
Mm,
Now, if we look at the first point, they're saying that the derivative is non-zero. First point says that f from Rn to Rn is such that bf A, this is invertible, and F is injective. Now, if we try to look for counter example in R, so in R, this will be F from R to R,
You mean
such that,
second option that was for surjective
sorry, the second option,
or injective. F.
They're
Oh,
saying
correct.
that
Okay.
the derivative is invertible, but the surjectivity is of the function f.
Okay.
That's not for the derivative. The surjectivity, this is f.
Oh, I switch one and two option in my copy, so I confused. Okay.
Maybe I would have written it opposite. I don't remember.
Okay,
What?
doesn't.
Hmm.
But
Okay. So now if we try to look for some counter example for a point first, that means we need in R. So that means we need a function which such that its derivative is
is
non-zero
inverse.
everywhere,
Mm,
and it is not injective. That means there are two distinct points such that at both the
it's
points the function is taking same value. That's what we mean by not injective. You know?
hmm, it was zero.
So is it possible that the function's derivative is not zero everywhere? Because whenever we are passing through one point and we want to come back to that point, anyways,
There,
you'll have to go through derivative to be zero.
if that point is sharp, oh, then that sharp point is not differentiable.
Not differentiable. Eh? It should be differentiable everywhere with non-zero derivative. So finding
Hmm.
such example in R is not possible. Then we'll look for R2. In R2, we
Yeah.
can find some example. In R2, if can you think of some example? F from R2 to R2 such
Uh,
that the F A determinant is non-zero for every A in R2 and F is not injective.
I have one example, but
Hmm?
this example, this example didn't come in my mind just by seeing the question. I copied from ChatGPT.
Oh, the e power x cos y, e power x sin y.
Exactly.
Yeah. That is a standard example though. It comes because we need not injective, na? So that means we want the terms to repeat. And the best example
Hmm.
for that is the periodic function. We should look for periodic functions. And the way, yeah, the function f from, so that we take fxy, this is equal to e power x cos y, e power x sin y. You can look for some other example also. So eventually, this exponential helps us to see that the derivative will, the determinant of the derivative will be never zero. That's how this exponential function is helping us, and the trigonometric functions are helping us to show that the points, the values will be repeating. So eventually, that this will not be injective. So we know that at any point dfxy, the derivative at point xy, this is the Jacobian matrix, no?
Hmm.
So basically the gradient of first vector, then gradient of second vector.
Second vector.
So this will second component, second function. If this is f1, this is f2.
Hmm.
The standard way of finding the derivative del f2.
Then
Yeah. So this will be
e
e
power x
power
cos
x
y.
and power x minus sin y.
Minus equals.
E power x cos y. So eventually the determinant of this matrix will be e power 2x, because yeah, cos square y plus sin square y will be 1.
Mm-hmm.
So and this will never be 0. And
Mm-hmm.
f of x y plus 2k pi, this will be e power x cos y plus 2k pi e power x sin y plus 2k pi, which will always be equal to e to the power x cos y e to the power x sin, which is f of x comma y. And this is happening for every integer k. So eventually the function f is never injective. F can
Mm-hmm.
never be injective, even though its derivative is invertible at all
Yes.
points. So this is the main idea of the main aim of this problem is to tell you that the inverse function theorem gives us the local bijectiveness.
Mm. Yes.
Let's look at the this week 11 assignment. Some problems related to LT spaces. And yeah, next question we have. Suppose f is in mi, that means f is a measurable function. If f belongs to mi, that means it is a function defined on some set I and it is a measurable function. Under which of the following assumptions can you conclude that the function is in Li?
Then third question also of week 6.
Third question. Let me see. Week 6.
Week 6. Which of the following sets can be locally expressed as graphs?
Okay. Yeah, I saw that. It was in week 6 only. I think we did some problems related to this graph. Okay, I'll just explain it. Which
Mhm.
the I think this axis and unit sphere so we did na. Eventually that would
Yes.
give us a manifold.
Yes, you need to spare it.
And for the case of axis, we won't be able to define a function because eventually that will be a multi-valued function at point 0.
Yes, at intersection point. Or
Hmm.
option C in D.
C and D are not that clear to me also, but
Will
can
be implicit function theorem, I think.
so you have any idea how to use implicit function theorem to prove this?
Mm,
Used as graphs.
mm, mm.
So implicit function theorem tells us that in what case you can make it a graph. How to discard it.
Mm. Oh yes, yeah. Started then.
Discarding is an issue.
Yes.
No? Because if we can find a function, that's good. But showing that we can never find a function, or you can find some counter example. Suppose for some examples, we are not able to find any function.
Mm.
Okay. X and y axis. in R2. The set of zeros, maybe because the graph should be a smooth function. No? Was there any condition for smoothness?
Mm-hmm.
Yes. Set of zeros will have at the most n number of elements. Uh,
Of
hmm,
a polynomial. Polynomial and polynomial is smooth, I think.
Polynomial is smooth, but we say that we can plot the set of points. This set is equal to some graph if we can find some smooth function f such that the set of points this is equal to x comma fx.
Um,
What is the condition on this f?
F is CK smooth.
It should be smooth, no?
Yes, yes.
And a smooth function can either take just one value. No, if it is piecewise, the domain is disconnected. Two variables.
Yes.
These two we did earlier. Set of zero. Suppose we have a polynomial. This is next to the power minus one next to the power minus one y upon 12. Sorry? So, I think the problem will be that this polynomial will eventually have some finite number of this set S will have some finite number of elements. So if suppose this was a graph, then that means there is exist a function f that takes value at x1 sub y1 at x2 y2 and so on. And I think the problem will be about the smoothness because this is kind of a discrete function.
Mm.
It is defined at some specific points. Other at rest of the points we don't know. I don't know what will happen at x1 minus epsilon and x1 plus epsilon.
Mm.
Okay, I'll look at it. I'll share that file if I could find some solution to this, some explanation. Eventually, this will are
Okay,
not
ma'am.
graph. Yeah, I'll have to look how to show that they will not be graph. Uh, Try it and then share the same handwritten notes if I could get the exact explanation. This graph and manifolds are already complicated.
Mm.
Even I get confused. Okay, then next we have
First question of week 7.
week 7. That was also related to manifolds, na?
Yes, yes, it is also.
That also I'll see later. I'll have to check that.
Okay, ma'am.
Okay, then we have this week 11, na?
Yes.
Suppose F is in MI, then under which condition we can conclude that this function is in Li. That is, if this integral over I mod f, this is finite. The first one says that f is bounded. So in the definition of L1, this mod should be taken or not? Which definition you have done? Because when we talk about LP spaces, we take this modulus. But when we are talking about,
What are you asking, ma'am? What are you asking?
what do you mean by function f belonging to Li?
Lm is Lebesgue integrable. So
Just
f is
integrable, just integrable or integrable with this modulus?
just integral.
Okay,
It's f is equal to u minus v.
okay. Okay, that's L1 space. Yeah, when we talk about L1 space, in that case, it's modulus. I was getting confused. Okay. So the first point says that when f is bounded, now since we don't know anything about this function, this set I, this can be some unbounded set also. Uh,
Yeah.
Mod f is bounded. Then we have this set I is bounded, saying that mod f, this belongs to Li. So which of the following do you think is clearly incorrect?
Fourth option is clearly correct, but
Correct, okay.
what
So
is this?
fourth, why? Because f is always less than equal to mod f.
Hmm.
So eventually this will be less than equal to this. And now since this integral of mod f is finite, therefore the function is integrable. Okay. Then what about the other options?
Hmm.
Can we say that first one will always be correct?
It's bounded then. If fx is equal to constant function over unbounded interval.
Yeah, in that case there will be problem. If suppose I take
Yeah.
fx, f is from, suppose f is from 0 comma infinity to
X equal to 1.
whatever, and fx equals to 1 for every x, this is I. In that case, integral over I, suppose if it is integrable, so this will be measure of I. And since this interval is unbounded, its measure is infinity or not defined. This implies f is not, or we can write f,
Yes.
f does not belong to Li. What about the second option?
The same thing, I think.
Same example will work. And the third one, now they're saying that okay, we give you that a condition that this I is bounded.
Hmm. But we can find I bounded, but function.
Yeah, now we'll look for some function which is unbounded in some bounded domain.
So 1 by x if
1 by x, because we know that 1 by x is measurable. That you should try yourself to see how the function fx equals to fx. Now if I define f from close interval 0 comma 1 to r, f of x, in fact I can define it something like this. This is equal to 1 by x when x is non-zero and some constant at 0. This will always be measurable. F is F belongs to M, close interval 0 to 1. But yeah, clearly this integral 0 to 1, 1 by x dx, this is not finite. The function blows up near 0. So therefore,
mm,
here, first and second are incorrect. And from here, the third option is incorrect as well.
it 0 will take 1.
Yeah, you can take any constant value. That won't affect the measurability of the function because at one point it won't hinder. Okay, this is week 11. No?
Yes.
Next question is, which of the following sets are measurable?
Yes.
See, the first option is clearly a nonsense. It is already given that a set of measure 0.
Mm,
So
second is also.
by measure you have just done the Lebesgue measure, na?
Yes.
No other measure. Okay. Sure. The following sets are measurable. So this is a property called the completeness of a measure. So since you have done just the Lebesgue measure, Lebesgue measure is a complete measure. Complete measure space is a measure space where the subset of the where the every subset of a zero measure set is also measurable. So that's a very good property of the Lebesgue measure. That's why our second option is also correct. Any set of measure 0. This is clearly, they are saying it has a measure. Then we have
Completeness of what do you say, man? The property name
uh,
of the property.
completeness of a measure space. So
Mm,
so here your measure space is just Lebesgue measure space defined on the subset on power set of real numbers. No?
yes.
There are some other measures also that need not be complete. Then
Mm,
we'll work on those measure space and try to complete them in some
so
ways.
some restriction or some.
Yeah, yeah. Any subset of a set with measure 0. So therefore, by that property, this is also correct. Then we have any interval,
Mm,
and then the difference a minus b of two measurable sets a and b. So when do we say that a set is measurable? Basically, if the infimum
integral.
of have you done this definition of measure, Lebesgue measure? Let me just write. If this infimum of summation Lik k from 1 to infinity, where this A is a subset of, if I take a set A and then I look for the set of intervals that covers this A. Suppose Ik is a collection of intervals such that this union Ik is containing A, then I take the length of those intervals, because length of interval is always finite. We know that length of a finite, yeah, anyways, length of a bounded interval. So in when all such collections,
It's a
when I
measure
take
of it.
their summation, yeah, yeah, have you done this definition? If this
Yes,
is
ma'am.
finite, then we
In
say,
university class.
yeah, yeah, then we say A
Mhm.
is measurable. So yeah, any interval covers itself, so eventually the interval will also be measurable. And what about the difference?
Yes, ma'am.
What about the difference?
Yeah, difference is also because
Yeah, eventually you can use the same set of
collection
cover
of
intervals.
measurable set
Is forms a sigma algebra,
is
right?
a sigma algebra. Yes.
Yes, yes, yes. Okay, then that means you have well basic information related to measure theory. Okay. So yeah, this question is fine. No? Next we
Mm.
have, which of the following is true about functions in Li and L2I?
Mm. So Lebesgue integrable and square
Hmm.
integrable.
Li and L2I. So the first one says that if f is a function which is integrable, then if f is integrable, then its square, then f belongs to L2I as well. That means if
Li is a subset of a
fi is finite, then should it imply that its square will also be finite?
mode of f is two.
Yeah, square taking, because square is always positive, no? So taking modulus or not, that's fine.
Mm-hmm.
So is it true? And
No,
if not, can you find some example?
in book postal book there is an example. Fx is
Yes.
equal to x to the power minus half
Yeah, 1 by root x, no?
a1 root x. It's
Because
0
1
to
by
1.
root x in 0 to 1 is integrable, but its square will be 1 by x. Let's see.
Mhm. Option C just definition, I think.
If f is in L2, then f2 is in L1. Yeah, f square. This will be in Li. And the fourth one, any function that is in both L1, Li and L2I must be bounded.
This is an issue.
Yeah, that need not be true. We can look for some example for that. First, let's start with the first part. If I take f from open 0 comma 1 to r, f of x, this is equal to 1 by root x, In that case, we know that 0 to 1 root x dx, this is 2 root x, no? And this is obviously finite.
Yes.
But that means f belongs to Li, but its square, okay? So the integration of 1 by x is ln x, and it has problem at 0. At 0, it goes to minus infinity, no? So this is not.
Mm,
So f does not belong to L to I. Therefore, the first option is incorrect. Then second, it says that if f belongs to L to I, if the square is integrable, then the function should be integrable as well. So can you find some example for counter example for this?
1 by x
Yeah, it's square. 1 by x square will be integrable.
means 1 to infinity.
Okay. If I take f from 1 to infinity to r, f of x equals to 1 by x, then f square, this is 1 to infinity 1 by x
Square.
square. This is x to the power minus 1.
Min-
This one,
Minus
infinity. Yeah, this will be finite, but 1 to infinity 1 by x dx. This will again have log term. This will go to infinity. Okay, therefore the second option is incorrect. The third one is clearly the definition. If f belongs to L to I, that means integral I f square. And since this is positive always, I can take the modulus also. This is finite. This implies f belongs to. Sorry, we need to. That's
f square belongs to Li.
that means f square belongs to L. Therefore,
Um,
the option is correct. Okay, let's look for some example such that the function is integrable, its square is integrable, but the function is not bounded. So I take f x to be something 1 upon x to the power 1 by 3. This is clearly unbounded. Is it integrable? Yeah, this power will be positive, no? So this is finite.
mhm.
What about its square? By 3. 2 by 3 is also less than 1, so this will also be integrable. X to the power minus 2 by 3 upon where it's 1 by 3, 3 minus 1 is 2 by 3. This will be plus 1, which
1 by
is
3.
4, 0 to 1, whatever it is. Since the power of x is positive, so
Positive.
this will be also finite. Therefore, f belongs to Li. From here, f belongs to L square I, L2I. But yeah, clearly this function is not bounded in open interval 0 to 1.
So, ma'am,
Hmm?
we are checking that simple integration whenever it exists, then it directly becomes a Lebesgue integrable. We are not.
Yeah, because
Like,
we know that every Riemann integrable function is Lebesgue integrable. No? All these
mm,
things are Riemann integrability.
Oh, so all the formula that integration of sin x is cos x, these are remaining
Riemann
approach.
integration.
Oh,
Yes, yeah.
okay.
Whatever you learned in your high school.
Mm,
Did
it's
it?
clear.
In school, you must have heard, your teachers must have told you that not every function is integrable. While finding derivative, you might find derivative of almost every function, whatever the class of functions you knew till 12th standard. But then your teachers must have told that integration is a bit different. Every function need not be integrable.
Yes.
Hmm. So in order to overcome that problem, went to the Lebesgue integration. Also, you must have studied some improper integrals.
Yes, improper integrals.
Okay. So yeah, I'll look for those manifold problem. Otherwise, I think till here it's fine.
Yes.
Okay. So when is your exam?
26, I think. 26 October month.
26th October.
And, and exam will be offline and pay and paper.
That's good.
That's good.
Yeah,
I don't know
that
how questions will be asked.
yeah, there I think they'll be asking subjective questions, so you won't be getting such assignment type of problems. You should
Oh,
practice. Yeah, that's why they're taking offline exam, na? The way you give in your university exams.
mm, I thought that they will ask theorem and proof. There are a lot of theorems.
Yeah, they might ask. You never know. Okay, then all the best for your exam. This was our last session. I'll try to solve those problems also. If I could, I'll share that file. Otherwise, yeah, this much I'll share.
And ma'am, in what course in next session you will
I
um,
don't know. I don't know. Because I don't know what courses will be floating next semester.
um, this was a very good session and we are very
Yeah,
lucky to have you as our
this was good
mentor.
experience for me also. Otherwise, generally students don't attend these classes. It's like talking to walls.
These are some guests. They are coming and they're think these are guests or other
I think
students.
no, I think they are someone who are checking whether the sessions are going on or not.
Oh,
Maybe because they are just joining for a few seconds, no?
yes.
Mm, might be. Okay then. Hopefully we'll meet in some other course next semester.
Any
Okay,
suggestion,
anyways,
ma'am?
any suggestion is like what suggestion you want? I'll tell you to just love the subject, love whatever you are doing, do with your whole heart. That's the enjoy the beauty of mathematics. That's it. Yeah. Okay, then you have my email if you want, if you have any doubt, you can just mail me. I'll try to
Yes,
help. Okay, then.
yes,
Thank
ma'am.
you.
Thank you, ma'am.
Okay.